Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're talking about intermolecular forces. Now, what are intermolecular forces? Well, what is an inter-school sports? It is sports between two schools. So what do you think intermolecular forces are? Forces between two molecules. Here I've got a whole lot of marbles. Let's pretend they are molecules. You see how if I push them together, they have a tendency to wander away. Now, I especially think molecules are always moving because they have kinetic energy. So there's a whole lot of shaking going on with these molecules. They're always shaking and moving except when they reach absolute zero. Now this would represent a gas. So let's show you what a liquid might look like. If I take a little bit of dough, which is flour and water, and I were to stick these marbles together with some dough, like this. Now there's a force between the marbles, and we could liken that to an intermolecular force, and that's kind of keeping these marbles together. Now, do you see a property which comes from intermolecular forces? It is, if this represents a liquid, it's free to flow, but how quickly or slowly it flows, in other words, how well it keeps its shape, the liquid, is called its viscosity. So that's one of the physical properties that we are going to talk about when we talk about intermolecular forces, because intermolecular forces give rise to the properties of solids, liquids, and gases. And it gives rise to properties such as their melting point, boiling point, their vapor pressure, their viscosity, etc. So you see where we have a situation here where we have fairly weak intermolecular forces. The marbles can flow a little bit past each other, and that we call a liquid. Now, yesterday I took some of that dough, the same dough, and I let it set, and here we have a little pyramid. A little pyramid of marbles, and you see how it sticks together quite nicely. This little pyramid here of marbles. So that would represent a solid, where the intermolecular forces are much higher than they are in liquids, where they kind of stick together, and in gases, where there's very little intermolecular force. Now, there are three types of intermolecular forces. We have our Thunderballs Forces. Thunderballs Forces, which include London forces, otherwise known as dispersion forces, and then we have dipole-dipole forces, which are part of our Thunderballs forces, and these are weakish forces, very weak. If you have a scale that's about 1, dipole-dipole forces about 2, twice as strong as London forces. And then we come to hydrogen bonds, which are about 12 times stronger. They can be many more times. It all depends on the structure of the actual molecules. But let us first examine what is meant by Thunderballs forces, and London forces in particular. Here we have, let us say it's an atom, like a hydrogen atom. There's the nucleus, which is positive, and the popcorn inside this clear bottle. Let that represent the electrons in the bottle, the electron orbital or its shell, its energy level even. So but let's say its orbital. Now, the electrons can be anywhere inside its orbital, but let's just suppose that the electrons happen to be, as they move around, more concentrated on this side, and another hydrogen atom comes along where its electrons, or popcorn, are evenly distributed inside the orbital. Now this is my question for you. Here we have a concentration of electrons. Electrons are positive or negative? They are negative. And here they come close to another hydrogen atom where the electrons are evenly distributed. Now what do you think these negatives, which happen to be here on your left, what do you think they're going to do to those electrons? Are they going to attract them or repel them? And the answer is, like charges repel. So the popcorn is going to move away to that side. So do you see what we have here? Now, I'm going to try and put this down. What do we have here? We have a collection of electrons here, which makes this atom overall negative on this side, but it's chased away the electrons. So the electrons are chased to this side of this hydrogen atom, and this becomes overall negative there, but look what's left behind. The positive nucleus. So this positive nucleus is attracted to those negative electrons, and that creates a force of attraction between the two hydrogen atoms. So that would be an example of our London or dispersion forces. Now just use this as an example. We know that hydrogen atoms always occur in pairs, and we know that hydrogen is a diatomic gas. But I'm just saying this applies to any and all atoms where you can have the electrons happening to be on one side of the atom, of the orbital, and we call that delta negative or slightly negative on this side. And it comes to a neutral atom, and those electrons chase away those electrons, leaving your positive nucleus close, and that forms a slight attraction. Likewise, that can be, the electrons could be on that side, this could be neutral. So what do you think the popcorn's going to do? Well, look at it. This side of the atom is slightly positive, delta plus. So it's going to attract this atom's electrons to this side. And so we get an attraction, and this can happen like this. Each time it changes, there's still an attraction between the two atoms or molecules. So, and in fact, the atoms can synchronize the way the electrons move so that the electrons are always almost performing this little dance which keeps a force of attraction between the two atoms. So that is the explanation of London or dispersion forces. And those types of forces are very diffuse. If this is, for example, two methane molecules, this is your carbon and the match heads are your hydrogens, you can get London or dispersion forces between these hydrogens, doing exactly what I've described there. The hydrogens can synchronize their electrons or get the electrons so that this one's positive, this one's negative, and then there's a force of attraction. And that is why methane, if you force them together under pressure or cool them, they can turn into a liquid due to London or dispersion forces. But this is a fairly weak force, and therefore we've got to press them together. They don't want to stick together, so we've got to have a very low, we have a very high pressure or a very low boiling point for these two molecules. Now dipole-dipole is almost similar to this. That is where we don't have a temporary shift of the electrons. We have a more permanent shift of the electrons. The electrons are almost a molecule that has got more electrons shifted one way than the other. Now, dipole attraction is almost like a north magnet attracted to a south magnet. And these magnets are permanent, and therefore we can get a fairly understandably easy way that these attract each other. There's a positive, there's a negative, there's a Coulombic force, Coulomb's law, a coulombic force between one, say you had something that is slightly ionic positive, something that is slightly ionic negative, and the two molecules are going to be held together by this coulombic force of attraction between positive and negative. And that's a permanent polarity, as opposed to here, London forces, where it's changing all the time and creating a very weak force. And then last of all, we come to our hydrogen bonds. Now, how do we explain hydrogen bonding? Well, it is a fairly strong force. And it occurs, obviously, where what element is present? And that is where hydrogen is present. But it's got to be present with a very electronegative atom. So hydrogen with, for example, hydrogen with oxygen, that's an electronegative element. Or hydrogen with nitrogen, or hydrogen with fluorine. And those are all electronegative atoms. Now, what happens in this case? Well, let's have a look. Here is a table of the electronegativities. The electronegativity of hydrogen is 2.1. That refers to how much does hydrogen love electrons, in its simplest terms. And hydrogen loves its electrons 2.1 times. This is just they're all comparable to each other. Whereas oxygen loves electrons, so look how the electronegativity changes. We've got hydrogen 2.1, carbon 2.5, almost the same, nitrogen 3, oxygen 3.5, fluorine 4. Now all these values you get on your BFF or best physics friend, the periodic table, and there it will be drawn on the left, probably on your periodic table with a symbol there, and there's your electronegativity values. Now those do mean something. They mean how much does each atom love its electrons. Now look what happens when you team up something that loves its electrons 2.1 times with, say, oxygen, which loves its electrons 3.5 times, which is a lot more. Nearly double, but not quite. So when hydrogen bonds with oxygen, remember your Lewis structure, it shares a pair of electrons because they are non-metal and non-metal. So that is a covalent bond. But which one loves the shared pair more? The oxygen. So although they share the electrons sit more closely to the oxygen. So we say the oxygen becomes delta negative and the hydrogen becomes delta positive or slightly positive. So this side becomes slightly negative, that side becomes slightly positive. So the electrons, if I were to draw an arrow, are shifted more towards the oxygen side. Let's have a look the same with hydrogen and nitrogen. Now nitrogen is 3. So the shared pair of electrons would be not as close to the nitrogen as they are to the oxygen. So although the nitrogen would be delta negative or slightly negative, and the hydrogen would be delta positive or slightly positive, this wouldn't be as positive or as negative as in the case of hydrogen and oxygen. But look, how does this result in a bond? Well, if we have something that has got, there's our water molecule, and this has pulled the electrons like this towards the oxygen. These are becoming slightly positive, but this has become slightly negative. Now what if we bring another water molecule here, where we've got a hydrogen, an oxygen, and another hydrogen there. This hydrogen is also slightly positive, and here we're getting a bond between this slightly negative and that's slightly positive.